Hi everybody, my name is Ben Hunt. I'm from Carnegie Mellon, so just to orient you, we're here right now, somewhere in the shadow of the Cathedral of Learning. This is Carnegie Mellon, which is that way, so about a 5-minute walk. So today I'm going to tell you about some experiments that we did last year. The title is Quantum Metal and Ising Superconductivity in Two-Dimensional Niobium Diselenide. So the essence of the talk is going to be about superconductivity in 2 dimensions. So before I begin, I just wanted to mention that a lot of this work was really driven by Adam Sen, who's now a professor at Waterloo, and it was done in the labs of Corey Dean and Abhay Pasupathy. Okay, so 2-dimensional superconductivity has been very prominent in condensed matter physics recently. Partially because there's a real interest in topological superconductivity, some issues in strontium ruthenate and making, Majorana fermions out of taking topological insulators and S-wave superconductors and putting them together. Somewhat related, there have been a number of new systems that have been discovered recently. So people have finally managed to take, say, a bilayer of graphene and intercalate it with some sodium atoms or some I think they're sodium atoms. And they've also taken lithium atoms and absorbed them on monolayer graphene. So they've found new ways of making 2-dimensional superconductors. And of course, there's the enduring issues of high temperature, interfacial, electric field-induced superconductivity in 2 dimensions. So this has relevance to, say, Jeremy's LAO-STO systems or iron selenide on STO. And anyway, a whole grab bag of very interesting topics in 2D superconductivity. Okay, so this is sort of the scope of what's going on these days. But I'm going to take a step back for this talk and ask a much more fundamental question. And that question is, what kinds of electronic states are even possible in 2D? Okay, so for a very long time, our thinking in condensed matter was driven by this very famous paper about the scaling theory of localization. And this is the thing to remember about this paper. These people predicted that in 2 dimensions, there can be no true metallic behavior. Okay? This is basically due to electron localization by disorder. Okay? This idea was for non-interacting electrons, but if we now allow electrons to interact, as we just heard in that very nice talk previous to mine, you can get very interesting states. So you can get something like a Mott insulator where the insulating state is actually driven by Coulomb repulsion rather than by this localization idea. And of course, you can get superconductors as well. So you can get, the thing that I'm going to be talking about today is basically these fluffy superconductors, as Martin Zweierlein described them, where electrons will pair up in these time-reverse pairs of electrons will pair up to form Cooper pairs. And then they can condense into a superconducting state in which all of the constituent particles occupy the same ground state and have the same quantum phase. Okay? It turns out that it's actually very, very hard in the t=0 limit actually to come up with any other phases. So even the metallic phase that you're used to thinking about, that we're all used to thinking about much more, it's very difficult to come up with a theory for a metallic phase in 2 dimensions. And so for a long time, again, and this is like from the 1990s, in 2 dimensions anyway, the prevailing idea was that you could only go from, say, a superconductor to an insulator. So here's a very classic paper from Alan Goldman's group in which they measure the resistance versus temperature of a 2-dimensional metallic film. And they can basically tune from this superconducting transition to the insulator by tuning the disorder, right? And this metallic phase, so some finite resistance at t=0, only prevails for a very, very, very small range of this sort of phase diagram. This superconductor insulator transition can also be driven by a magnetic field, a perpendicular magnetic field, which is itself a kind of disorder. So this sort of paradigm for a quantum phase transition was recognized by the 2015 Buckley Prize to these people for their experimental and theoretical efforts in this regard. What gets kind of brushed under the rug, though, is that actually at the same time as discovering this superconductor insulator transition, in some films, what they would actually see is a very, very large range of not superconductor or insulator, but a metallic phase as t goes to 0. And this was actually sort of rediscovered in the 1990s in Stanford and other places by Aaron Kapitolnik's group in amorphous films of molybdenum germanium. So what seemed to be very important here was that you had this disorder on the atomic scale that had something to do with the presence of this metallic state. And remarkably, to this day, there's never really been agreement about the microscopic nature of this metallic state. I told you before, it's actually quite difficult to come up with a theory for a metallic state as t goes to 0, despite a significant amount of firepower, intellectual firepower thrown at this problem. Okay? So this is the outline of my talk. I doubt I'll get through all of it, but I'm going to tell you about our new approach to making 2D superconductors from a van der Waals material and our sort of rediscovery of this strange metallic state in the t=0 limit. And if I have time, I'll get to this interesting contemporary topic of Ising superconductivity. Okay, so by now, I hope everybody is familiar with graphene. Maybe you're sick of it. But the way that you make graphene is you take a stack of, or you take graphite, which is a van der Waals material, and you peel it off, you exfoliate it with a piece of Scotch tape. Still, we do this. And what you may not know is that there's an entire family of layered compounds that we can explore with which that you can actually use also to create two-dimensional materials. And we now have techniques by which you can basically peel off layers of any superconductor or semiconductor metal that you want, stack them up in a nice stack that Andre Geim calls a van der Waals heterostructure. And remarkably, we can make interfaces that are atomically flat and clean. So it goes from kind of a Friday afternoon type activity to being able to do some pretty serious research with these van der Waals heterostructures. Okay? So the subject of the talk today is this one, which is a classic superconductor, niobium diselenide. Okay? So if you've heard of these transition metal dichalcogenides at all, you've probably heard of molybdenum disulfide or tungsten diselenide, which are the semiconductors. But if you go one column over in the periodic table and you take away one of the d electrons in the system, what you end up with is a system that's highly hole-doped, right? So here's a calculation of the electronic bands that, I'm missing all the references here. I think I chose a bad color. But this is from Di Zhao's group, actually from one of his students that calculated the electronic bands. And here you can see the Fermi level intersects a couple of different pockets of the Brillouin zone. And because of this very strong hole doping, this basically leads to a variety of correlated phases in these group 5 transition metal dichalcogenides. So bulk niobium diselenide, for example, has 2 very interesting phases, a charge density wave phase that onsets at about 33 Kelvin, and a superconducting phase that onsets at 7 Kelvin. Okay? There have been a number of activities in this area over over the past several decades, but soon after the discovery of graphene around 2009, some groups actually tried to start making this two-dimensional superconductor. And what they found is that they can actually suppress the transition temperature a little bit by thinning it to, say, 10 nanometers. But as you try to get down to the monolayer limit, it actually starts insulating. Okay? This was a bit of a surprise because well before we started working on it, in 1972, this gentleman, Frind, studied niobium diselenide. And apparently, he got down to the monolayer limit. So this is a monolayer here, and it apparently worked for him. And the only thing that we could find was that these experiments were all carried out in British Columbia air, which is a very beautiful part of the world, but I'm not sure it's that good. So we had to devise a more kind of brute force way of doing this. So what we ended up doing was taking the niobium diselenide and doing this exfoliation inside of a glove box. So our strategy was to exfoliate in the glove box and then encapsulate it with an insulator, protect it with an insulator, and also simultaneously make contact to it. So as of yesterday, we now have this facility over at Carnegie Mellon, so you're welcome to come over and have a look at it if you have a minute. But So anyway, this is what our device looked like. It was formerly insulating in the bilayer limit. Now we can produce a very nice superconductor with a transition temperature of about 5 Kelvin. And the important thing to note about this compared to the disordered samples previously is that this sample is extremely clean. It's crystalline, right? It's a single crystal of niobium diselenide. It has only about 75 ohms per square resistance in the normal state. And so we're really in the clean limit of a superconductor where the mean free path is much longer, well, somewhat longer than the coherence length, okay? This shows the extreme magnetic anisotropy of a two-dimensional superconductor. So if we apply a magnetic field perpendicular, we can quench the superconductor very easily. So this is Hc2 versus T. This is because of the orbital effect. As you heard from the last talk, the way that the magnetic field will penetrate the samples, or the rotation field in that case, is in vortices. And so when there are enough vortices in the system, you quench the superconductor, and that's this line. Now, if you put a magnetic field in plane, because it's a true 2D superconductor, you can't actually form vortices to screen the magnetic field. And so the mechanism for destruction of superconductivity in that case is flipping the spin in the Cooper pair. And in that case, you can see that the perpendicular Hc2 is much, much larger. So this anisotropy really shows us that we're in the 2D limit, okay? Okay, so that was sort of our understanding of the nature of the 2D superconductivity in this niobium diselenide. Now I'd like to turn to sort of our new observations. So this isn't a great color scale, I guess, for this projector, but what you should be able to see here is a large red region. This is, by the way, the resistance of the sample. A large red region where we see the normal state, where we've quenched the superconductor, right? In a normal transition, what you would expect would be to see this entire region kind of a dark blue color, a resistive state, right? A superconducting state. But what you see is actually quite a large range of resistance in this, where we would expect to see the superconducting state. And if you take some line cuts along here, this is now on 1/T versus log R axes to bring out the Arrhenius behavior. But what you can see is that, in fact, as a function of magnetic field, the resistance is not 0 down here, but it saturates to a finite value as we go to low temperature on the right-hand side, okay? So if we compare back with this amorphous molybdenum germanium film, you can see that the data look very similar, right? There's this behavior where the resistance at low temperature increases as we increase the magnetic field, okay? So the main difference I wanted to point out again is that these were in amorphous films, and this re-observation of this metallic state is in this a very low disorder crystalline superconductor that we produced, okay? So just some more details about this. If we look at the high temperature regime, the resistance is actually activated. And we can understand that looking back at these papers from the 1990s in terms of basically a logarithmic dependence of this activation energy on magnetic field. That has to do with the properties of the vortex lattice and creating dislocation, anti-dislocation pairs in the vortex lattice. But this is pretty well understood. And then this is the feature that I want you to remember about the talk, which is that the resistance remains finite and independent of temperature as we go to low temperatures. The behavior with magnetic field is the important thing, an important new contribution that we made. And what we see is that for a number of cuts down here as a function of magnetic field, the behavior is actually that of a power law, right? So the resistance versus H goes like something like H to the H cubed or something like that. So if I were to draw a phase diagram, this is essentially what the field versus temperature phase diagram looks like for our 2D superconductor. Up here is the normal state that I showed you before. This TAF phase is the thermally assisted flux flow. That's the activated behavior. Importantly, we do observe a two-dimensional superconducting phase at finite magnetic field, but that's a very, very low field. That's only about 0.2 Tesla or so. And then for a very large, I would say relative to the old observations, for a large area of the phase diagram, we observe this quantum metallic phase, okay? How am I doing? So let's go back. I had mentioned that there's never been really agreement about the microscopic nature of this metallic phase that we see. So the new ingredients that we've thrown in the mix are that we see it in a very, very clean superconductor, and that we observe this power law behavior. Okay? So there's sort of two prominent models that have kind of come to the fore from these various theories. One is that it's some sort of tunneling of vortices at low temperatures. And then the vortices, so sort of the system may break up into puddles of superconductor and normal, and the vortices may tunnel, say, between those various puddles. And if the vortices are tunneling and sort of coupling to a fermionic bath, then maybe you could get some dissipation and some finite resistance. Maybe a more radical theory, I don't know how else to characterize it, is the idea that actually what's happened is that the superconductors become completely phase incoherent, and that you have a bath of Cooper pairs that have lost their phase coherence but are essentially still paired. And this idea of a Bose metal, basically a bath of free bosons, has been around for a long time. But I should note that our data actually do seem to agree with the predictions of that theory, which are that the resistance at low temperature should scale as a power law and not exponentially. So I would not say that we have completely observed the Bose metal in this case. Our data seem to point towards this idea. But certainly there are new challenges for experiment. And 3 minutes, OK. Particularly spatial probes. So we can now access the two-dimensional superconductor quite easily with scanned probes. So this may be, looking at, say, shot noise tunneling or something might be a very easy way to confirm whether we're seeing 2E charge or E charge. I should point out that these metallic phases seem to be showing up more and more these days. Again, I lost the reference here, but here's a paper from Japan in which they've created a 2D superconductor by ionic liquid gating a semiconductor. And indeed, they see a very similar behavior to ours. OK, I'm not going to have time to talk about this last topic, but I'll just summarize it in one slide. Whereas this quantum metal phase that we saw before is way down here, the normal phase, which we've quenched with a perpendicular magnetic field, is up here. If we apply an in-plane field, in fact, the superconductivity, in stark contrast to what we see in a perpendicular field, in a parallel field, the superconductivity survives up to 30 Tesla. Okay, so that's actually quite a remarkable thing, considering for experts that the Pauli limit is down here. So the Pauli limit is what you would expect from a naive picture of spin flipping in a 2D superconductor. So in our system, the superconductivity actually survives much, much, much higher than the Pauli limit. I don't really have time to go into why that is. But yeah, so this is sort of the takeaway message that the superconductivity in our 2D system survives 30 Tesla in plane, but it yields to this metallic state at 1/100th of that field, so around 300 millitesla. OK, let me just summarize my talk. Basically, so what I told you about was, from a technical point of view, a really good way of making 2D superconductors is to do it in this glove box. Otherwise, basically, they oxidize and they disappear. So we can use our van der Waals techniques to build up basically heterostructures of 2D superconductors and metals or whatever, or interfaces between superconductors and semiconductors. From a scientific point of view, we sort of rediscovered this quantum metallic phase in the ultra-clean limit, very low disordered system. And we also showed that superconductivity is very, very robust to in-plane magnetic fields. So in the future, what we would like to look at is, at least for the in-plane fields, there's a number of ideas. One was alluded to in the last talk, that it's possible that in the superconducting phase at very, very high magnetic fields, you might see one of these FFLO, Full-de-Ferrel-Larkinov-Chinnikov phases. So that's with the in-plane field. For the out-of-plane field in the quantum metallic state, we'd, of course, like to look at it with tunneling experiments in which we might be able to actually see what the spectrum looks like, see if it looks like a pseudogap-like phase, like in the high TCs, something like that. And again, I sort of missed the references here, unfortunately. But there's some very interesting ideas that in this kind of high Zeeman energy superconducting phase, we might actually be able to see some sort of form of topological superconductivity. So that's basically it. So thank you very much for your attention.